Hello, hi everyone. Great to see so many of you attending this wonderful series of schools. I've been to Bamberg and to Bologna, and I guess Abu Dhabi also counts. They had a winter version not that long ago, and then UCL. So great to be here. So I'm going to talk about work that I am more kind of starting rather than have done, but I think it's more probably relevant to what you guys are all thinking about. So that's why I chose this topic. So I'm talking about human-machine social systems. And what I mean by machines would be kind of a variety of either embodied or virtual scripts or algorithms, or here you can think also about robots, self-driving vehicles, and so on. And so these are, they can have various degrees of autonomy, right? So they could be anything from kind of managed to completely autonomous. They can be very general, like large language model, or they could be specialized, such as say agricultural drones. But some of the ideas I'm talking about are kind of encompassing all kinds of intelligent machines, right? Most of my research would involve online scripts, bots, algorithms, but we can also think of here about robots. Now, what I want to emphasize that the explosion of these machines, intelligent machines recently, emphasizes the fact we have to think of them as just a multitude of different intelligent machines. Also, we should recognize that they're heterogeneous, so they're different, right? Like, so there's all kinds of sorts of machines. And most importantly, what I want to emphasize is the fact that these are social machines. So even if they're not designed to interact with each other, they end up interacting just because they operate in the same social environment. Now, what this leads me to kind of propose is that we should treat these actors and agents these machines as actors and agents who interact on par with humans. So basically, they interact in similar ways as humans, and we can analyze them the same way we have analyzed humans for a couple of centuries now, right? So now this is not a new idea in a sense. So you might be familiar with the fields of human-computer interaction, the fields of social computing, computer-supported cooperative work, where we have looked at how a human would interact with a computer, with an interface, with algorithms often, so recommender or sorting algorithms. Now, kind of, this is my view, and it's a bit cartoonish, but a lot of these approaches have focused on the machine as a medium or interface, so something that mediates our social interactions. Now, there are kind of more macro level approaches, mainly from sociology, social and science technology studies, digital sociology, where they have kind of focused on machines as an infrastructure, on environment, right? Some kind of and even when you think about it, a lot of kind of recommender systems or algorithmic bias kind of thinks about these algorithms as an infrastructure, right? Like something that again kind of specifies and constrains our decisions. What I'm suggesting here is to treat the machines as actors or agents. And again, this is not necessarily a new idea. We have artificial intelligence, right? We get focused on the agent as a human-like intelligence with much more focus on the cognitive abilities rather than the social interactions. We have multi-agent systems, so a field in engineering that looks at systems of bots or drones and coordination among them, for instance, or cooperation. And macro level, we can talk here about the technological singularity, but where this idea of human-machine social systems is situated is somewhere here between micro and macro. So it's focusing on the emergence of social structure and social patterns from the interactions between humans and machines at a network level, right? So the idea is we have multi-humans, human and machine, and predict or understand the outcomes in these social systems.
Sorry to interrupt.
Yes.
In sharing for the recording, for some reason appears with a different shape on the screen. So it appears correctly on the main screen, but not on the screen share.
Okay, so.
That's that for the recording.
Okay, but let me try. Maybe I can share the whole desktop. Let's see if that will fix it though. Okay. Is that any better?
Perfect.
Okay, excellent. Okay. Right. Okay, good, great that we had a pause. Okay, so why do we care about this? Well, importantly, there are differences between human-machine social systems, or this kind of hybrid system they're also being called, and what we have studied for the last couple of centuries, human-only systems. And here we're talking about, difference at what I would call the first order. So this would be, just compositional difference. So the fact that we introduce different kind of actors, we will get different kind of outcomes in these systems, right? So machines, are not the same as humans yet, and they behave differently. So when we have different kinds of actors, we'll get different outcomes. Now, there are also second order differences. And now here we're focusing on the interactions and the idea that we will have human-machine interactions that would be different than human-human interactions. I think that's normal. If a human knows that they're interacting with a machine, they would behave differently. But also, as I mentioned, machines would be interacting with each other, even if they're not designed to be social. These would occur, and we need to understand these too. Now, finally, there are also third-order differences. And here the idea is that just merely knowledge of that there are machines among us, so to say, would change human behavior and human interactions, right? So even if they're not direct interactions, there will be these indirect kind of trickle-down effects. Now, what I'll do is that I have selected two projects from my past work where they were not necessarily actually one of them triggered this thinking about human-machine interaction. The second one wasn't necessarily from this paradigm, but it still concerns interactions between machines and humans and machines, just to illustrate kind of how I've been approaching this and just to give you some empirical results, I guess. But as I mentioned, this is kind of a direction I'll be taking more in the future. So come back a couple of years later and maybe I'll have some new results about this. Okay, so the first project I want to talk about is bots on Wikipedia. So this is a project I did with Taha Yasseri, Ruth Garcia Gavilanis, and Luciano Floridi. So I was a postdoc at the Oxford Internet Institute. That was a while ago. The project came out in 2017. So it's a bit, old, but also we actually analyzed data until roughly 2011, which was when the bots on Wikipedia were most active. So what are bots on Wikipedia? So they are described as automated or semi-automated tools that carry out repetitive and mundane tasks to maintain the pages of Wikipedia. So these are not sophisticated, AI agents. These are very simple scripts, several lines long, that would be doing kind of crawling through the different pages and making small changes such as fixing a typo, making references, linking one language version of Wikipedia to another. Right? Nothing sophisticated. Here, they're not designed to interact. Now, some of these bots are non-editing, but for this paper, we focused on what are known as editing bots. So these are bots that edit articles, so they make changes to the articles. And some of them would be undoing vandalism, some of them would be enforcing bans, checking spelling, and so on. I have plotted here, a word cloud, 2017, these were, fashionable. So a word cloud of the different bots in our data set. And the size of the words is scaled by the number of edits they've done. And mainly to illustrate the fact that there's an ecology of different bots, right? So there's hundreds of them, and they're active to different extent. We also have kind of a long enough period of observation of 6+ years. So now if we look at the number of bots compared to the number of human users, so the human users are with blue here, the bots are with pink, but you don't see them because they're very few, right? So we're talking about several hundred compared to, say, 17 million editors on Wikipedia over the period in English Wikipedia, over the period we study. We study 13 different language versions of Wikipedia. If we look at the number of edits, however, the bots now are kind of disproportionately active, and this makes sense, right? They don't get tired. They just, keep going 24/7, slowly but steadily covering all of Wikipedia. Now here what we do is we focus on reverts. So these are edits that undo the edit of someone else. Now for human users, these most often are kind of edits where there is a kind of an undo button in a sense, so revert button that you can press, and often these are used to say remove vandal content or to remove the edits that you might disagree with or like big deletes and so on, right? But for the bots here, these are most likely unintended reverts, right? Like, so there's a bot that makes changes, and then another one comes and makes its own changes, but these changes that it makes are actually undoing the work of someone else. So when we look now here at the average number of reverts for between humans on top and bots on bottom, we can see that bots have like on average about 100 reverts each, right? So that's a large number. Again, given how active they are, it's not maybe that consequential, but there's some inefficiency here, and these are unintended. All of these bots are approved, they're tagged, they intend to improve Wikipedia, but they end up undoing each other's work to some extent. So we wanted to look at these kind of interactions, so between two bots undoing each other's work, and we wanted to compare these interactions to human-human reverts. So here we are plotting a sample of some of the bot reverts. So what we do is we will plot time over on the x-axis, and on the y-axis, you can think of this as the reverts, the number of times I reverts J minus the number of times J reverts I, right? So we have a line that goes up if I reverts J, but then goes down if J reverts I. And so these are bot reverts. These are some of the human reverts, and we can already see that they're quite different. Now, there's some things also we can see. The fact that, for instance, from 2005, when Wikipedia, when the bot started coming out, we have these bots kind of start reverting each other, and some of these interactions continue for years, right? Up until 2010. So we have cases where two bots would be undoing each other's work kind of back and forth over years. While for humans, we have for bits kind of shorter spikes, and usually they're more one-sided in the sense that one editor would be reverting another one without reciprocity. So to quantify these, we came up with 3 features. One is latency, so basically the time period between successive reverts. One is imbalance. Think of this as like who wins in the end. Is it just one person who undoes the work of others, or is it is it even? And one is reciprocity, that looks more kind of at the micro scale. Is there a lot of back and forth, or is it smoother, right? So to look at latency, we can see that for human reverts, we have quite different characteristic timescales compared to the bot reverts. So for instance, we have a peak here, it's 2 minutes and 24 hours. 24 hours makes sense, the diurnal cycle, right? You go maybe check your favorite Wikipedia articles, every evening after work, and that's when you do activity. 2 minutes is because a lot of human editors use tools that notify them for changes on particular articles they're monitoring, so they can react immediately. After a year, it seems like most kind of interactions are disappearing, right? Maybe that's some kind of cycle of activity. For bots, we have a peak at 1 month, right? And this has to do with the fact that bots are kind of crawling slowly and not to overwhelm the servers. And so they, about a month later, they encounter each other. Now, we took these 3 features and put them in a k-means algorithm with just the goal to kind of identify different kinds of interaction trajectories and quantify the differences. So we identified 4 different trajectories. So we call them fast, unbalanced, slow, unbalanced, somewhat balanced, and then well-balanced. And we can see what we already saw with the naked eye is that human interactions tend to be kind of more one-sided. So one editor would revert another one. And when we inspected this further, we found that typically there are also status effect in the sense that it will be a more senior editor undoing the work of a more junior editor, not necessarily vandals. We tried to remove vandals as much as we could, but there were even kind of more senior, more status effects here. For bots, we have this kind of more balanced ones where it will kind of go back and forth over long periods of time. There's not necessarily a winner, and these will kind of continue undetected. Again, this is not surprising because these are unintentional interactions, right? They're not designed to, these bots are not designed to interact with each other, and hence they don't exhibit these social signatures that social interactions exhibit. Now, when we published this article, some of the media picked it up and got, very excited in a negative way, right? Like, so talking about, the Sun, especially, computer programs will soon begin to fight each other and it could lead to disaster. And the title we had was Even Good Bots Fight. But I just wanted to kind of wrap this up to saying that, even fighting bots are good, and to emphasize the fact that, if you go through the article, we have a much more measured kind of a conclusion compared to the media. And the idea here is that, we detect some occasional disagreements. They're not as significant compared on the kind of the volume of positive activity, the positive contributions the bots do. And the reason for these disagreements is not some kind of, intentional war, but it's because of kind of distributed development and also maybe complicated rules and just kind of disagreements emerging from different editors interpreting the rules in different ways, coming up with their own bots to implement them, and these bots disagreeing de facto. Now, later, two researchers from Wikipedia, they kind of took a bit more qualitative approach, and they looked at what is the reason for this. So they kind of redid our study quantitatively, but then also wanted to understand what's going on. And so the conclusion is that most of these would be classified as routine, productive, or collaborative work, right? Like they're not as problematic. And also, let's not forget that conflict is not necessarily problematic, right? Like often, truth emerges when people argue. So it's not as negative that media made it sound. There was only one case where it was kind of interesting, where two human editors were using their bots to basically fight a proxy war, right? So they were like, seeking them against each other, pretty much. But that was an exception rather than the rule. And I also wanted to emphasize the fact that and there are other studies that have looked at the ecology of bots on Wikipedia, particularly when it comes to vandalism detection. And there is a study that looked at kind of the random outage of one particular vandalism detection bot that was the most prolific one. And they studied how does Wikipedia adapt to this. And their conclusion was that it was exactly this diversity and kind of distributed different kinds of tools that people were using that helped the system be resilient in face of kind of these random outages. So diversity and distributed development is actually quite important and helps Wikipedia function. Now, most of these bots have disappeared from Wikipedia. They have moved to Wikidata, and so I'm actually hoping to revisit and see what's going on there. Although I think they have been a bit more streamlined now, so this kind of interaction might be happening less often. Now, this was one example of bot interactions and how they compare to human interactions. I wanted also to give you another example where we have bots. And so this is multiplayer online games where players would purchase or find on the deep web, find some cheat code that gives them an advantage when they play a game. So for this particular project with a student of mine, Jeannie Kim, we studied a multiplayer online game known as PlayerUnknown's Battleground. So short is PUBG. That's how they're referring to it. So it's a first-person shooter game where you get randomly matched, sometimes in teams, but 100 players get randomly matched. They're dropped on a field. And it's a battle royale game where basically the last one standing wins the game, or the last team standing wins the game. It's team mode, and the field starts compressing so that players are forced to interact with each other. Otherwise, right, like you might just wait it out in a bush, right, like until everyone gets tired. Now in the game, this is how, usually this is the beginning of the game, everyone gets dropped on this field, and that's before the game starts. This is, I'm showing you here like one cheat code that shows how participants or players who have cheat codes might experience this. So in this particular case, I think it was some kind of automatic aiming code that allows you to, always shoot on target and potentially also see behind opaque boundaries, right? So basically ways in which you circumvent the rules, the physics of the game so that you get an advantage. Now, in this particular case, we were looking at a particular one server from Kakao Games, so in Korea, and they have implemented a way in which you can report cheaters, suspected cheaters, and there are also other ways in which you can, if you get killed, you can continue spectating the game through the eyes of your killer. So that could be another way in which you can detect that some cheating happens. And so what Kakao Games does is that, or used to do, I'm not sure what's the state now, but they would, if there is a report, they would investigate and they would ban the user. Now, this is actually quite extreme. There are many kind of taggings on Steam of cheaters, but usually you just get tagged, you don't get banned. In this case, your account gets banned. So we had the list of banned users, basically. We didn't know when they started cheating, so we had to estimate that roughly based on behavior, right? Like on their shooting patterns, but we knew who was confirmed cheater. So now why do people cheat? Well, actually, I think that's a psychological and philosophical question, I'd say. But what we saw was that they get banned, so it's quite risky, right? You might lose money, you might lose, definitely lose reputation or some kind of, points one. But cheating, I guess, makes the game more exciting for you. So it lets you kill more. So here we show the cheaters with pink, and that's the average kill ratio. So they tend to kill more players. And also they kill them in faster succession, right? Like, so there's like a shorter time between kills. And that's what we use to attempt to detect when the confirmed cheaters started cheating. So we have very few cheaters, so 0.3% after all, right? Like, so it's not that many, but what we were interested in is how cheating spreads. And in particularly, we use the kind of theory of the contagion of social behavior that distinguished between what we can call third-party influence. So this idea is that if I see people behave in a certain way, I tend to imitate it, copy it, and I tend to, I might be more likely to adopt this behavior. So imagine for cheating, for example, if you observe that there is a cheater in the game and they, having fun, killing a lot, you might want to do the same, right? Like it sounds like it makes the game more exciting. Now, there is another mechanism when it comes to social behavior, so behavior oriented towards someone else. And so this one we call generalized reciprocity. And this is, this idea is that you pay it forward, right? Like, so if someone behaves in a certain way towards you, you might pay it forward. Now here, think, both positive and negative. In this case, if I get killed by a cheater, I maybe out of, revenge, I might start cheating, even though I'm unlikely to pay it back to the person because a lot of these interactions are anonymous, or you get randomly matched, so the chances of encountering the same player are pretty small. But you might, feel negative affect here and just, go on a rampage, killing, cheating and killing. Now, when it comes to antisocial behavior, we call these kind of contagions through observation and contagions or, witnessing crime, so to say, right? Like, or witnessing a killing in this case, or cheating, and contagions through victimization. So becoming a victim and adopting the behavior. Here, of course, we focus on adopting cheating. It's kind of interesting because it's antisocial behavior, but, of course, it's a game where killing is the social behavior, right? So it's a bit ironic. But, as a kind of cheating, still in this community is considered antisocial. And of course, this could be valid for other kinds of antisocial as well as pro-social behavior, online trolling, academic cheating, bullying, and so on, right? But here we're only looking at cheating. Now, here is a network of one game where with pink, we have 3 cheaters. Now, this is handpicked. It's very unusual to get 3 cheaters. Most games don't have a cheater or have one. With green, so with black and pink, we show who killed whom. So from the killer to the victim. Thicker lines mean that the killing happened later in the game. And you can see here there's a kind of a loop here, which means that the player did something to explode themselves. So they're responsible for their own death. With green, we show who observed a cheater. So this is a very peculiar network, right? Because you can only die once, in a sense. You cannot kill after you're dead. So it's not a typical social network, right? There is a kind of a sequencing of the interactions too. There could be only one winner, or one person standing. In the team mode, you can have a few others from the team members. The way we approach this is we looked at event sequences. So these you can think of them as kind of the signature of a contagion event, where if you get killed by a cheater, or you get to observe someone cheating, then you start cheating. Now, of course, that doesn't mean causality, right? Like this could happen just because, like cheaters, someone will be observing cheaters, people will get killed by a cheater, and maybe you came across a cheating code in some other means, but that's a precondition for contagion, right? Like just the temporal ordering of these events. And so the minimum is that we want to find these signatures of contagion, but then we want to come up with a baseline against which we can, say to what extent these kind of patterns, event sequences, occur more often than you would expect just by random chance. So the way we do this is that we were given a particular game, as here, we would randomize the interactions between kind of the sequence of events, right? Because this network is also very complex. We cannot really come up with some model of it. So what we do is we basically relabel the nodes. And now think of this as an alternative history of where, all right, you weren't hiding here, you were hiding there, and now you happen to be the victim and not the other player, right? So something like that. So here actually I'm showing this, what we did here, but for a team mode game. So here the colors represent different teams. Now teams are a bit complex because there is self-selection, so it's possible to select your team members. And as you know, when we study contagion, selection is one of the biggest confounders of that. That in this case, we cannot tell whether just because my friend started cheating, I start cheating, hence I have, contracted the cheating bug, or whether something makes us both more likely to be friends and to be cheaters, right? And so in this case, I tend to select into a cheating group. So what we do here in this case is that we would randomize within the team, and we will also fix the positions of the cheaters because they tend to kill more, so they don't want to undo that part of the structure. Right? As you can see, they're much more they're more central here, so that's the whole point of getting these cheating codes. Okay, so we have our empirical observation. We count these event sequences. We randomize, count again, randomize, count again. So we get like a distribution of what we would expect if we had alternative histories. And the idea is that if we have more contagion happening, so kind of some abnormal pattern of contagion, then we would observe more of these event sequences in the empirical network than in a alternative scenario network. So when we do that, we look now at those who are victims and those who observe. Now here, this shows the likelihood of observing the counts that we have in the empirical network compared to the expectation from the randomized networks. So think of it as a p value, right? So here what we find is that those who both observe and are victims of cheaters are more likely to cheat, or rather, we can interpret it as the event sequences in which someone who both observes and cheats starts cheating are more common in the empirical network than in the randomized networks. And when we do this, looking at the number of times you are a victim or observe a cheater, then we also see that there is this effect of where if you observe and suffer multiple times, you're more likely to adopt cheating. Okay, so these were two examples where I tried to show you first that in Wikipedia, we can look at unintentional bot-bot interactions. We found that despite these bots being good, they're designed to cooperate, they might end up disagreeing by accident. But we shouldn't forget that this kind of the reason for this disagreement, the diversity and the kind of distributed development of these bots is pretty important for the resilience of the system, right, and the robustness of the systems to outside attacks. So it's not necessarily a bad thing, and there is this kind of conflict between small-scale individual or small time-scale interactions versus the global picture and the resilience of the system. Now, for cheating bots in multiplayer games, we saw again that some kind of, I guess, contradiction is that there are players who suffer from this, right? Like, so if you get killed by a cheater, the game is not as interesting to you, right? Like you might, quit playing. That's why also gaming companies try to reduce cheating because it just drives away players. But what we found is that actually those who are victims and observe common cheating tend to actually more likely to adopt cheating, right? So in a sense that kind of unexpectedly, we have the victims being the ones who propagate cheating. Now, these are obviously stand in a larger landscape of social interactions. So cheating in multiplayer games is or multiplayer games in general is an example of, I guess, a social situation of competition, right? Like different players competing to be the last one standing. Markets are another very good example of a competition system. And there is a very prominent I guess, example of human-machine hybrid systems, and these are markets, so particularly algorithmic traders on markets, and then high-frequency markets, where arguably there are no humans left. It's mainly algorithms acting there. So we have reviewed quite a bit of literature around this, and so one of the findings is that these algorithms, and especially high-frequency trading algorithms, they're the short-term impact on the system is on the market is that they improve the efficiency of the market because they help price discovery, right? Like, so they find the optimal prices in a sense, and hence the market is more efficient. However, because a lot of these algorithms react to the same kind of information and they react very fast, they end up exhibiting herding behavior, and this leads to quite often to instabilities. So you might have heard about a flash crash. Multiple of them have happened by now, of where you have this just extremely rapid kind of changes in market pricing because of all these kind of herding behavior, like buying or selling. So there's this conflict between short-term positive impact and then the long-term instability that they drive, they introduce in the market. Wikipedia editor is an example where we have cooperation between both humans and bots. And there are other situations where this can be studied. So I think personal AI assistants could be another examples where there could be more research about this. Now, there is also situations of coordinations where we have to find ways to coordinate among each other and with machines. And traffic, I think, is a good example, and especially human-driven vehicles and self-driving vehicles. And now here, there's also some precedents of where there have been some unexpected consequences. Particularly, I have heard of one case where in Austin, Texas, there was a private company that was moving its fleet of self-driving vehicles from one location to another. And so there were like 30 or so vehicles. And what happened is that they basically just got into a traffic jam, and there was no way for them to coordinate and to communicate with each other and get out of it, right? Like until humans had to come in and manually move the cars. And so this is an example of where these, we have these machines that I think in principle, maybe we're not there yet, but in principle, they're supposed to improve safety in driving, in traffic, right? That I think we all agree that they'll probably follow the rules better than we do, right? Like they're probably better drivers. They might react faster once we have figured out all the issues. But in this case, they might also have these unintended consequences where if we don't design them to communicate with each other or with human drivers, we might not be able to resolve certain situations, right? Like we humans often communicate, with curses, with, middle fingers, with, waving and so on, right? But it is communication. And with these self-driving vehicles, this is currently difficult or impossible. Now, there is also the situation of contagion, particularly contagion of information and misinformation. So this is actually a field where we have had quite a lot of study, particularly with Twitter data, looking at social bots on Twitter. And so one of the, it's huge literature, but one of the findings there is that these bots tend to be marginal. So they tend to be on the periphery of social networks. They're not very well connected. Until recently, also maybe before LLMs, they weren't usually generating content. So they would be just retweeting, right? Like, so they were not producing misinformation. They would just retweet others. However, and they would typically, be kind of weakly influential, right? Like they wouldn't be very visible. However, they still, arguably have affected the spread of misinformation. And so one argument is that they do that because they manage to connect to a central actor. And so even if they are kind of weakly influential in their own social network, the fact that they can influence by accident like one central actor means that this can spread throughout. And actually, there's an argument that it's precisely the fact that they're weakly influential, they don't drive away their followers, right? Because we all have had kind of, an uncle or whatever, like a friend from primary school who posts such, extreme things that we disagree with and we unfollow them, right? But if you have something a bit more subtle where you wouldn't unfollow them, actually, they might in the long term influence you more. And the other power that these social media bots have is that they exploit human weaknesses, right? Like, so they exploit things such as confirmation bias, moral outrage, and they, that's how they can spread misinformation. So the argument is that, they don't create the misinformation, they just spread it, right? And by exploiting our weaknesses. Now, there is also the field of collective decision-making where we have quite a lot of literature coming out about hybrid decision-making. So clinical diagnosis is one big field, organizational decision-making, hybrid forecasting. I'm aware of one example in citizen science. So that was not far away from here, Oxford, Zooniverse. So it's a citizen science platform where volunteers, non-experts, would volunteer their time to classify galaxies from space imagery or animals from heat trap cameras in national parks, for instance, or in the wilderness. And so what they have done is that they have experimented with incorporating these volunteers' kind of wisdom of the crowd decisions with algorithms. And so what they found is that, in general, kind of having this diversity and introducing algorithms help the accuracy and discovery. However, it drives away the volunteers, right? Like they kind of feel less useful and they participate less, right? So again, there is this kind of trade-off between, in the short term, we might improve accuracy, but in the long term, if we drive away the volunteers, then we might actually be worse off. So hopefully this kind of all these examples try to emphasize that outcomes in hybrid systems could be emergent, could be unexpected, can be unintended. And so there is a need to understand these better and to study to what extent they differ from human-only systems. Do we need even humans, for instance? Maybe, removing the volunteers, maybe the algorithms are good enough and diverse algorithms would do the same job and so on, right? Like, so all these questions. Now, what does this mean for a more broader kind of picture. So I'm a social scientist. So of course, the first thing I want to do is to study this kind of human machine social systems. So this is actually based on a paper in Nature Human Behavior. It's a perspective literature review paper called A New Sociology of Humans and Machines. Actually, I'm a sociologist, but I disagree with the title because I would say new social science, because we covered a lot of economics, finance, and also sociology is not just that, right? Like many sociologists would disagree with calling only this sociology. But we can have many of the methods that we have used to study humans now study hybrid social systems. In terms of AI design, what we try to emphasize in this paper is the fact that we need to study these human-machine and machine-machine interactions, and we need to train these machines on them, right? So far we have we train, for example, self-driving vehicles, we train them on human traffic. But as we know, humans might behave differently if they see a driverless car. And so we need to be able to account for the differences. And there's obviously no need for sensitivity to culture and context. I think driving is a very good example of where if you train something on, say, American drivers, this might not work well in places like India, Rome, or Indonesia. Now, in terms of policy, what we tried to emphasize in the paper was, and it kind of emerged from the examples, is that diversity is very important. So we reviewed some kind of studies. Some are empirical, observational, but some were experimental. And often the finding was that the machines are most useful, so they improve outcomes when they're different from humans. So when they behave in non-human ways, right? Like they randomize, for example, perfectly, or they don't adapt, or they persist with the same action, or they shift, or whatever it is, right? Like, so the moment we try to emulate humans, we don't do it currently perfectly, and then the machines are kind of failing. If we do it perfectly, then do we need even machines? If we know how to make humans, right? So maybe we don't need artificial humans. Now, as I mentioned, this is this started with the BotBot paper, where we started thinking about these unintentional interactions. We revisited it with Taha Yasseri for this paper, where we tried to kind of pretty much review the literature, where we stand. And so next, I'm hoping to work on this. So I was very lucky to get an ERC grant for a project called HumanIt, which is to study human-machine social systems and how they differ from human-human and machine-machine systems. And the idea is to look at, to use all the methods that I have worked with. So that includes controlled online experiments, agent-based modeling, and also online observations of online communities, including field experiments in online communities, and to study this more systematically. And so, for instance, to give you an example, one experiment we can do is to look at how humans make decisions or get influenced by other humans or by bots in small groups where there could be the minority or majority in reference to bots, for instance, and where there might be agreement or disagreement between the humans and or the bots, right? Like, so what is more influential, right? Like kind of agreement between the bots, does this can increase the outgroup bias, or is it something else that's going on, like some kind of authority, for example, bias, where you might assume that the machines know better. We can scale this up using agent-based models and look at now larger networks, where we can look at, say, the positioning of the bots in the network and whether that influences the spread of information or social influence. We can also do online experiments in larger groups where we can try that. And finally, I already mentioned about Wikipedia. Reddit is another massive online community where there are endemic bots with and a variety of them, and a lot of them are visible and people interact with them. So that's another excellent playground to study these topics. Gaming, I mentioned, and eBay also is an interesting system where there are a lot of automatic sniping algorithms, right? Like where, in a sense, they're machines compared to humans who who bid in a very different way. So there are many others. Gaming, I think, is a very interesting area where you can look at interactions between NPCs and players, and also cheating bots, as we've done. Okay, so 2 years, maybe I'll be able to to show some results. Currently, the project just started 1st of May, and my postdocs are starting in September and October, so not much. We're currently doing a field experiment on Reddit, actually, but I don't have results. Thank you.